Our research objective is to create an infrastructure climbing robot that's able to reach difficult spaces and navigate dangerous environments. It must have an independent autonomous navigation that's able to localize itself in 3D and traverse obstacles in its way. It must also have a high cargo capacity while staying lightweight itself with a rigid structure and overall having a relatively low cost for mass production in the long term. And we achieve this through Vertipaw, as it's the first quadrupedal robot capable of delivering loads greater than 4 kilograms on any planar surface. And it does this by using an active vacuum suction system that's able to maintain over 150 kilograms stationary. But this suction power also allows it to adapt to rougher surfaces. The 3D localization is facilitated with LiDAR, and it's able to automatically transition planes, whether it's the wall to the ground, or the ground to the wall, or the wall to the roof, or any other angle. The LiDAR is able to detect that, and it also uses a PID feedback loop for foot positioning and potential slippage. And we're currently still working on the adaptable autonomous navigation system. Our general hardware configuration consists of 4 legs that's held together with a carbon fiber rod frame with PETG clamps and struts for rigidity. We power it with a 12-volt power supply or a LiPo battery if we want it to be mobile. And the current suction pad can actually reach around 17 psi within 5 seconds. And because the suction pad has an area of around 30 inches squared, this pad experiences over 500 pounds of force. And that's pretty astronomical considering we want to 3D print this with PETG. So we had to use finite element analysis to reinforce it. And we also use neoprene rubber strips on the outside that allows for minimal leakage. This allows the system to be unpowered for hours on end. And what this means is that the robot can stay onto the wall and keep its position for, like, let's say an hour or two before it needs to be actuated again, suctioned again. And this allows for overnight maintenance with minimal power. But also because of how high the suction pad strength is, our current carrying capacity is actually limited by our servo motor power, which we aim to address with counter springing in the next slide. So counter springing is needed because servo motors alone cannot pull up the entire weight of the robot against gravity. And in order to facilitate that, we use counter springing that closes the center linkage in order to pull up the robot. And we also have 2 other types of springing that allow for this. So first we have suction pad springing, and this removes the need for active suction pad angle actuation at the bottom of the lower leg. And while it's unsuctioned, this springing allows the foot to be within 15 degrees orthogonal to the lower leg. And this allows us to position the lower leg at the correct angle in order to transition planes without the need to change the suction pad angle manually. And while it's suctioned, it can rotate around 40 degrees about the rotation point, and this allows the quadruped to gate. And finally, we have one more type of springing, which is over-centering prevention springing on the leg, and this prevents the leg linkage from being locked into the wrong configuration. So if you solve the forward kinematics equations with the 2 motor angles, that can actually result in 2 different XYZ coordinate solutions depending on the configuration of the central linkage. So in order to prevent the leg linkage to go into over-center clamped position, we want it to stay unclamped. So we have the blue elastic bands that keep it tensioned in one certain configuration. Next, we use a Raspberry 4B for all the processing, and we created a custom relay transistor PCB that drives each vacuum pump through a 12-volt power supply. And each vacuum pump will drive 2 suction pads, and this is possible because there's never 2 pads on one side on like the surface at once during movement. So for example, if we set 1, 2 as the 2 front legs and 3, 4 as the back legs, 1 and 4 are powered, and 2 and 3 are powered simultaneously with 1 suction pump. So our inverse kinematics calculations are pretty standard. We do have an additional angle conversion because we use the upper linkage, but it's just derivable with basic trigonometry. And we're converting Cartesian coordinates, which is x, y, z, to theta 1, theta 2, which are servomotor angles, which is called inverse kinematics here. And with these inverse kinematics commands, we're able to send a function through, a mathematical function like a sine theta plus b, and we're able to draw out a series of points with the leg. And for example, for the gate, we have a sinusoidal rise forward and a linear retraction back. So it goes forward here, and then it pulls backwards in order to move forward. And for planar transitions, we use a sigmoid function, which is kind of like an S shape, and we pull that forward in order to tilt the robot back. And each one of these commands is multi-threaded for each leg, and sometimes it's offset by one period in order to maintain the balance of the robot. And we also have a queued state machine, and this stores requests and evaluates the system's current state to determine the ideal sequence of operations and determine whether or not we can continue to the next action, essentially. We use a LiDAR and a motor that rotates the LiDAR in order to map the surroundings. The first thing that we determine with these values is the wall distance. And to determine the horizontal distance from the wall, it's not as simple as just getting the LiDAR value directly, since we have to convert it through the cosine of the pitch angle that we determined through inverse kinematics. As for the rotation angle, our LiDAR will scan back and forth and create a function, and we take the derivative at 0 from the line of best fit to determine the angle phi from the orthogonal, and you can see it in diagram B here. And essentially we're finding where the distance is minimal, which is where it's orthogonal, and we'll rotate the robot to that angle phi. And lastly, we have the wall angle, and we will tilt the robot by changing y1 and y2 here. And this will allow the robots to identify the angle of the inclined walls and allow for adjustments for inverse kinematics. So this changes the functions that we use, the mathematical functions that we pass to the robot's dog. And for example, beneath 30 degrees, we actually don't even use the sigmoid function anymore. We just directly modify the sinusoidal curve and linear retraction by cutting off before the complete period of the sine graph. As for planar transitions, our robot is capable of rotating from 0 to 100 degrees, so that's more than enough for regular wall transitions, and it can move at a steady pace on horizontal surfaces of 0.161 meters per second, but on vertical surfaces, our velocity is limited by our suction flow rate, which is why it's only 0.065 meters per second. And the graphs are generated using the LiDAR values at the moment, and we have variability in scanning and walk pattern tilting, which creates these curves. In conclusion, our primary goal of carrying 4 kilograms was achieved. The suction force is still able to carry over 150 kilograms of practice, and this suction power allows for stationary and powered operations for extended periods of time. Our maximum movement speed is still primarily limited by foot positioning security and suction flow rate, and we may implement different planting procedures that's more than PID algorithms in the future that will plant with various forces for a secure hold. In the future, we want to improve the turning capabilities, as when we're planted on the wall, it's difficult for us to rotate, and this is all contingent upon the availability of higher capacity motors, since we may want to make a 3-degree freedom leg or a twist actuator. With these higher capacity motors, we could also improve the walking pace, and we will continue to use lightweight materials and optimize the leg linkage ratio to further enhance the robot's load-bearing capacity and overall efficiency. Furthermore, we are improving our software by developing novel pathfinding algorithms. We are deconstructing a 3D map into a single plane and treating each planar transition as a node to a new plane so that we can define an XYZ coordinates and a plane that will allow us to navigate in 3D but autonomously. Thank you.